In this video, we're going to explore the definite integral as area under the curve. So maybe a good place to start would be to discuss why we want to find area under the curve in the first place. Well, one reason is because we can find formulas for areas of various shapes, okay, any shape in the xy plane. As long as we can describe its boundaries as functions, we can use integration to develop formulas for the area. It also turns out that the same process that we use to find the area is what we use to find a function's antiderivative. And this means going backward from a derivative to the original function. And why would we want to do that? Well, just as a derivative represents the rate of change of a function, the antiderivative represents the amount of change of a function. And so we've explored for several months now how to go from a function to its derivative to find out how fast it's changing. And now what we can do is start with the derivative of a function and determine how much the original function is changing. So for example, if we know the velocity function v of t, we can find out how much the position is changing, x of t, by using integration. So here's the basic idea. We have this graph of a function y equals 10 minus x squared divided by 10, and that's represented by this blue curve. And we want to find the area of the region underneath the blue curve. And so one strategy would be to break up the area into rectangles, because rectangles are easy to find the areas of. It's just length times width. And then we could add up all of those rectangles and come up with an estimate for the area. And so let's see about doing that. If we start with 10 rectangles, then we get a picture that looks like this. And if you did all of the calculations, you would find the area was 71.5 units. Now notice that we have all of these little pieces that stick out here. And so we know that this looks like it's an overestimate of the area. And there's quite a bit of these rectangles that are sticking out here, and so we know that this estimate is going to be too high and probably not very close. So how could we get a better estimate? Well, if we allow our number of rectangles to increase, we get smaller rectangles, and what that ends up doing is making smaller errors. In other words, the rectangles stick out less from above the function because the rectangles are narrower. And so this number right here should be a better estimate of the area than what we had before. So extending that idea, we could go out to a larger number like n equals 100, and we can see now that the error in all of these pieces that are sticking out here is considerably smaller, and so this should be a pretty good approximation, pretty close. It's still going to be a little bit high, and it's not going to be exact. So how do we get the exact value? Let's look at dividing this region into 7 rectangles, and then we'll find their areas and add them up. We use this diagram to illustrate the basic idea, and then we can extend that out to larger numbers of rectangles. To get the total area, we need the areas of all the individual rectangles. So let's label each rectangle with a number that we'll call I, from I equals 1 to I equals 7. These rectangles span the interval of x equals 0 to x equals 10. Each rectangle occupies a subinterval of width delta x. So this is delta x, this is delta x, this is delta x, and so on. The height of each rectangle depends on where I am along the x-axis. For example, in this diagram, I'm using the height of the graph at the far left end of each rectangle as the rectangle's height. So in this rectangle, for example, I'm using the far left end of this subinterval as the height. Up to the graph, that's the height of the rectangle. As we'll see later, it really doesn't matter where we choose the height within each rectangle, but we'll stick with the left side for now. The width of each rectangle is delta x sub I, meaning the width of the ith subinterval, or the ith delta x. For that same value of I, the height of the rectangle is f of x sub I, where x sub I is some value of x in the ith subinterval. As we've seen, x sub I is going to be at the left end of that interval in this example. So, for the third rectangle, we have I equals 3, and delta x sub 3 is this rectangle's width. I've chosen x sub 3 to be the far left end of this rectangle, so that the height of this rectangle is f of x sub 3. The area then of this rectangle, of the third rectangle in this case, is the height f of x sub 3 times the width delta x sub 3. In order to get the total area of the 7 rectangles, we're going to add all 7 areas together. We're going to use sigma notation like this. Now to review, sigma notation says, using this symbol here, sigma, that we're going to be adding some number of terms here. Each of these terms is going to be an area in this case. We're going to start with the first, I equals 1, and we're going to calculate, using a formula, what a sub 1 is. And then we're going to change I equals 2 and find out the second one, I equals 3, and so on, all the way up to I equals 7. And we will add those together. Now the formula we're going to use, of course, is going to be that the area for each rectangle is going to be the height of the rectangle, f of x sub I, times its width. And we'll do this 7 times, from I equals 1 to I equals 7. Now, 7 rectangles is not going to give us a very accurate estimate for this region's area. What we need to do is increase the number of rectangles towards infinity. And this is represented by this limit notation that you see here. So we're now taking the limit as n goes to infinity of rectangles from I equals 1 up to whatever n happens to be. The bigger n is, the more rectangles we have, the smaller the delta x's are, and the better the estimate of the area is going to be. Now, we can work with this limit notation, but ultimately we're going to be using this notation here, which is what's called the definite integral of the function f of x from a to b. Okay, and this is your x value at the left end and your x value at the right end. For our function, a would be 0, b would be 10. Now notice how the different parts of this limit expression kind of line up with the definite integral. In fact, this delta x becomes dx in the limit, and this is basically the same dx that we've had in differential calculus as dy dx.